You guys, welcome back to my YouTube channel. We're still under fluid mechanics, which is N5. We've given question 4. Says, what is meant by the following terms regarding the flow of liquid? 4.1.1 potential energy, 4.1.2 pressure energy, 4.1.3 kinetic energy. Like potential energy, those things there. What regarding the flow of limit, what does it mean? All right, so okay, those, let me show you something. So potential energy, you can see the potential energy. The potential energy is the energy possessed by a liquid particles by virtue of its um, position. It's a potential, all right, not the pressure. Or remember that one that has a P, this is a pressure. That is for the static, or yeah, thing that is static. So what is the potential energy? It is the energy possessed by a liquid particles by virtue of its what position. So then pressure energy is the energy possessed by a liquid particle by virtue of its existing pressure. Like existing pressure then. Alright, so then we have this one. Kinetic energy. The kinetic energy is the energy possessed by the energy that possessed by a liquid particles by virtue of its motion or velocity. This is what we have there. Yeah, all right. We together. That is what we'll have so far. All right. So we can, let's just now do some calculations. Let's go to this now part. We are done with that. Let's hear 4.2 says the hydraulic system has a simple it has a simple tap. Check that those are tappers from a large diameter D1 to a smaller diameter during the raise of what of 3 meter at the static 2. The pressure the pressure the pressure at the entrance is that we've given the right is 200 kilopascal, and the velocity is 2 meters per second. The weight flow of the fluid is D is 197,499 Newton per second. All right, and the fluid has a relative density of that 0,98, and the velocity exit is 11,55 meters per second. The system has a head of 0. You see, the system has a head loss. The system has a head loss of this 0,5. Head loss of 0,5. All right, that is the head loss. Then says here 4.2.1 calculate the diameters, not only diameters of the hydraulic system. All right, to understand this part, this is a tapper pipe. Tapper pipe is a pipe that is it starts from bigger diameter. It becomes bigger. Is starting from sorry guys, what I've done there, sorry about that. All right, sorry about that. So the tapper pipe starts from a bigger diameter. then goes we'll have now from starts from bigger diameter, then it reduces, goes as it goes, it become more smaller, it end up with what, with a smaller diameter there. It's end up with what, with a smaller diameter. It's end up having what, a smaller diameter. So this is the pipe. All right, so now this pipe, the problem here is not placed exactly horizontal because there's a distance there. If you can check this pipe, this can trans I can just can you is like you can rotate it like that. This is like it is not completely horizontal. Let me just do it like this a little bit. I can say it's like that, a little bit like that. Alright, I can say it's like that. This distance from the horizontal, let me just say this final distance there can have 5 meters there. Alright, so obviously there will be fluid flowing there and discharge is there together. So alright, this is what we have anyway, so let us not waste time. There's 2.1 says the diameters. Alright, but let's take advantage of what we've given. We've given the weight flow. Remember, the weight flow is the same. Okay. We've given the weight flow. Remember, the weight flow at this point is the same as the weight flow at this point. The weight flow is the same, is like Q1 is equal to Q2. Similarly to mass flow, to weight flow, now even the weight flow will be like this. It respects the rate of flow. It goes like, even the mass flow, it goes like that. So it won't change. So we have the weight flow, right? So, but anyway, weight flow, let us start calculating. We have the weight flow. Let me find the density of the fluid first. The density of the fluid, we know given relative density. If you have given relative density, you'll multiply it by 1000. What is that relative density that we're given? We've given relative density here of 0, 0,89. So 0,89 multiplied by 1000. This is for water, will be 890 kg per cubic. Remember, it's measured in that per cubic meter. That is our density. So we also know that the weight flow must have some dot there on the top. Show this is a weight flow, is not just the weight. If you still remember the weight flow, I've said is the weight flow is given by the density multiplied by gravity multiplied by area. Let me say V1 area 1. At the in check, now I'm starting to calculate. Let me just say at the entry. This is the entry part. The entry. I'm looking at this part. I want this diameter and I will start there. Okay, let me start there. So we know we are given this guy where this we have calculated. We want, let us just calculate what the area. Okay, we want the area that we took it. So let us substitute. What is the weight flow? We've given the weight flow here. The weight flow is 197.5 499. That is our weight flow. Our weight flow there. Are we together? So since we have the weight flow, we'll take advantage of it. Let's take advantage of this weight flow. 750, 4. What is that? Is 99, right? Then the density here obviously is 890 times gravity 9,81 times the area. Let me just leave the area. Area 1, the velocity. Are we given the velocity? Yes, it was 2 at the pipe 1 at the entrance. If you want to see, we can see it here on the statement. D1 is small, right? There is, okay. We have this pressure at the entrance, and the velocity is this is 2 meters per second at the entrance. So that is what we have. So let us make area the subject. Making area the subject there, I'll have 750,499 divided by 890 times 9,81 times 2 divided by this. Alright, so we'll obtain the area there. Alright, let's try and obtain the area there. The area that we obtain. Where do I get this number? Sorry, this is 197,499. Where do I get that value actually? 197,499. This will give us the area, punching that 11,31 times 10 to the power of minus 3 meters squared. That is area, but we want the diameter. We know this guy, it's the same as pi over 4 d1 squared. So will be equals to what? To that 1131 times 10 power of minus 3. Then I want the diameter. d1 will be simply equals to what? Multiply by 4 that side. 4 multiplied by 1,31 times 10 power of minus 3. Then take the square root of all of these. Divide this by pi. Alright, so we'll have d1. Punching this, supposed to obtain your d1. Diameter 1 at the entry simply equals to 0,12 meter. Then if you want this in millimeter, will be 120 millimeter. That is what is d1. Similarly, we said is the same. Remember, I said this flow at 1, flow rate at q1 is equal to flow rate at 2. So we can say again, flow rate, just write 2 like that. We know it's given by what? Density, our gravity, area what now? 2. Remember, velocity 2. We actually at the end we want the area. Can make that area to the subject. Right, so we have area 2. So this is set is the same. Since it's the same as we will simply have 197,499. Nothing has changed. So here divide this by the density. There, the density of this substance there. It's 890 times gravity 9,81 times the velocity. What was that velocity at the exit part? Here the velocity at the exit they say it is 11,55 at the exit there. All right, multiply by 11,1155 there at the exit part. All these have area 2 must be equals to what? 1,956 times 10 to the power of minus 6, obviously. But we know that this area is equals to pi over 4 d squared, obviously is d2. 1,956 times 10 power of minus 6. Then you can have d2 will be the square root, will be 4 multiplied by 1,956 times 10 power of minus 6 divided by pi. Then we'll obtain the value there. So we'll obtain our value here. All right, therefore d2, what will be that d2? We'll have something like 0,0499 meter. Then millimeter, d2 will simply equals to 499. If you want, you can say 500 499 millimeter. You can approximately this. You will just show this. You can say this is it's approximately to 5. If you want, but here we are still fine. All right, even those the one who use scientific, they will be fine. There will be option 3 option there. You'll all right. There will be a range. So we got that diameter. So here we see the pressure at the exit. The pressure at the exit. We want the pressure here. What will help us there is Bernoulli's equation. Anyways, there is no other way. You can go around Bernoulli's equation. Know that Bernoulli's equation P1 over density gravity plus V1 squared over 2G plus Z1 must be dP2 over plus V2 squared 2G plus Z2. All right, so we want the exit pressure. Surely we are given P1. What will be the P1? P1 we're given here at the entrance pipe. The pressure, the 200 kilopascal is the pressure. The velocity is 2. The other one is that. All right. So, and then the head loss we have head loss. You see, head loss. So you'll add plus the head loss plus the head loss H loss. All right. Let's go now. The density we've seen there is 200. So we'll have what 200 times 10 to the power of 3 divided by the density. That substance there that we have used is 820. We took care that is 89. So how many? 890. 890. Remember the density there times gravity plus V1, it was 2. Squared is 2 multiplied by gravity, 9,81. All right. Then we have here, this must be equals to, okay, this will be 0. It's at the horizontal first. This one is at the base. Remember, the pipe is like this. This would be 0, but here we'll have the height of what? Of 5. I don't remember. Let's check with the 1P2. I will just check there. Here we still have 890 times 9,81. All right. Let me gravity plus the velocity 2, it's 1 comma, still remember that's 5 squared there, divide by 2 times 9,8. My 81 plus supposed to have now this. Let's check. It is 5. You see it's raised. The static, you see it's at a level there. They've given us is raised what? 3 meters. Oh, 3 high is not 5. Is 3. Is 3 meter high. Is 3. This is 3. So we have that the height there will be 3 plus the loss will be 3 plus the loss is 0,5. We've seen that loss here. If you don't believe, the head loss is 0,5 plus the head loss 0,5 for the head loss. So all this actually we want this. So it's a matter of calculating this, punching this on the calculator. Will have 22,97 plus punching this again. We'll have this to be 0,204. It's equal. Remember, this is simply 0. Here we have P. You'll take this is like having that. We'll have this to be 0,000 1145p. Right, P2. Remember, this is same as 1. You punch this on the calculator like that. We'll obtain this. Then plus, we have to punch this now on the calculator there. We have to punch those to obtain those. All right, will be plus, we punch this. Okay, let me just start by this. We have 6,799 plus that plus this 2 would be plus 3,5 like this. Yeah, it's 3,5. It cannot be 3, this will be 3,5. So that is what we have. So now since we have that, we can simply, okay, we have this on this side, subtract this on the other side. You have these 2,907 plus 0,204 minus these 2 minus 6,799 minus the 3.5. This must be equal to 0,01411 0,1145 P2. All right, then plug this there. What are we going to obtain there? If you have 2, 907 plus 0,204, right, minus this 6,799 minus 3.5. This will give you 12, we'll have 12, what here? 12,82. This must be equal to 0,001,145 P2. Then we have P2, you divide both sides by 0,01145, both sides, you know most the maths. Then if you do that, then why is supposed to show this? No. Then if you do that, you'll have P2. If you punch this, what is that we're gonna obtain there? What is that? We'll obtain 0,00. We have how many zeros there? 3 zeros. Okay, it is another 0, 3 zeros. After the comma we have 3 zeros, so 0,0001145. This will be 111, 825 kilopascal. Already I've written this in what? In kilopascal. So that is what we'll have there. That is the P2. All right. This will be, I've just verified that 12,8, but let me verify this. 5. All right, we still okay. It's right. It's okay. Yeah, we have obtained this. All right, that is P2. Now here we should determine the input power. The input is here in the inlet. Input will take the inlet, in the entry. All right, one, the input power. This we should determine the input power. So we have P in must be equals to what? We know this hydrodynamics will have H multiplied by the weight flow. We'll have the weight flow multiplied by this weight flow. All right. So, but H will be equals to what? Will be equals to P1, remember? Because we are using P1 because this is an input. If we are using that because it's an input, are we together? We're using that because we're dealing with an what? Input power. The one we have to use G plus V1 squared over 2G plus Z1. So this, it was 2000 unit times 10 power of 3 divided by density of 890 times 9,81. V, it was 2 times 9,81. This is simply 0. This is H. If we punch this, we'll obtain our H. We'll obtain H there. Alright, which will be 323,111 meter. Alright, so we have now P in. We know it's H multiplied by that. So we have 23,111. The weight flow, these were given, isn't it? We put it as 197,499. We're given that the weight flow. Punching this, will have P in there will be equals to what? It will be equals to 98,749. Right. DC can be 9. Okay, no. This I punched wrong. This is not correct. This would be 4, 6, 4, 5. All right, 4, 5, 6, 4, comma 399 watts. Power is measured in watts. The power is measured in watts. So this is an input power. If you want it in kilos, we'll divide this by 1000 before, 564 kilowatts. All right, so we have that. What again we can determine now? They want us to determine the output power. So I've discussed the output power. You must know that P out, the output power must be what? The input power minus the power loss. All right, minus P loss. This you'll get this from the head loss, from the head. So what will be power loss? Power loss is equals to head loss, right, multiply by the flow. Obviously, sometimes this will be what? H loss of what? Of the friction. But even the friction, still it's a head loss. All right, multiply by that. HF, this formula is one and the same thing. This is a friction, still it's a head loss due to friction, or in the pipe, still the head loss in the pipe. This is simple H. Our head loss there, it was 0,5, remember? Then multiply by this guy. We know that guy is 197,499. We are given with flow. Punching this, you'll obtain 98,7495. This must be in watts. Then this, if you want in kilowatts, you divide by 1000, will be 0,987495 kilowatt there. All right, you have that. So P out, as we have said, will be P loss minus P in. Is P in minus P loss. I want to say that P in minus P loss. Let me sort about that. It's P in input power minus power loss in the pipe, or power loss due to friction, or power loss there. We have this P in, which was 4.564 in kilowatts. So you can substitute this in kilowatts. The SI units must be the same. This is in kilowatts. If you use watts, you'll use this in watts. Also, the other one must be in watts, but I'll use them in kilowatts. Then I must use also this one must be in kilowatts, 0,0987495. This will be P out, will be what? This won't affect that much. Simply, this is just zeros. We'll still have 4, 4, 0.65 kilowatts. That is the output power. So thank you for watching. May you kindly subscribe to my YouTube channel and become the part of the family.